Hey everyone, let's talk for a second about cyclic groups. So this is section 6 in your book, and we sort of hinted at it at the end of last class. So I've got some definitions written down here. So if you have a group and an element of the group, then the cyclic subgroup generated by that element is this. So this is the notation for it, and you just take all powers of A, all positive powers, all negative powers. So just in case you've forgotten what it means to sort of take powers. So here's a convention that we've been using. So if we have a group G with star, we always have to specify what the operation is. But once we've stated what the operation is, we don't tend to always use the star unless there's more than one operation, like when, there's two groups involved and each one has its own operation or something like that. But if there's just this one operation, we tend to sort of drop using the star everywhere and just use the same type of notation that we use when the operation is multiplicative. So for example, we started off saying that if A was an element of the group, then A inverse, we wrote it like this, is A inverse. But using multiplicative notation, we can just write it this way. This doesn't mean 1 over A. That doesn't make any sense. Unless we happen to have, real numbers and regular multiplication, that sort of thing. This just means the inverse of A, for whatever this operation happens to be. Same thing for products. So if I have A, B in the group, we could either write A star B, that's sort of the normal notation, but we could also write A, B, and just leave the star off. If we write A, B, it's implied that we know what the operation is. It's the only operation we've been told of, so that's the one we're going to use. For repeated products, like let's suppose I wanted A star, A star, A star, A. Well, that's A operated on by itself 4 times. So we can just use that multiplicative notation, which would be, it should be A to the 4th power. So A to the 4th power is defined to mean take A and operate it by itself 4 times. Same thing with products of inverses. If I had A inverse with old notation, star A inverse, oops. I can just write that, that's A inverse times itself 3 times. So I can just write that as A to the minus 3 power. Or in other words, this was A to the minus 1 cubed. Okay, so we're just using the notation that we're used to using for multiplication, but it's going to mean something different depending on what the operation is for G. All right, so here's another specific example. So in the case where G is the symmetric group on n letters, if the operation is composition, I might have sigma be an element of this group, and I can write, if I do a sigma to the 5th power, I don't really mean sigma times itself 5 times. I mean sigma composed by itself 5 times. Because I've already specified composition as the operation. Okay, so with that in mind, let's think about this again. So what am I doing? I don't know what the operation is, but whatever it is, this means take your chosen value, your chosen element of the group, and do that operation by itself n times for every integer n. So that means, 0 times is going to be just the identity. 1 times is going to be A star A is going to be A squared. A inverse is going to be A to the minus 1, etc., A to the minus 2. So we're going to have A to all powers. This is just multiplying it by itself a bunch of times, or operating on it by itself a bunch of times. Okay, so in fact, let's think of this example. So let's consider, we want the cyclic subgroup. Oh yeah, one more thing. I'm calling it a subgroup, and that might seem bold because really I've just created a set, but I'm calling it a subgroup because at the end of last class period, we actually proved that this thing creates a group. It was kind of rushed, but it's in your notes and it's also in the book. Okay, so it really is a group. It's not just a set. It's a subgroup of the original group. Okay, so let's consider this particular example. So let's consider the cyclic subgroup generated by A. So the cyclic subgroup generated by 3 is going to be, I can write it as 3 to the n for every n in Z, But remember, that just means do the operation n times. So, and aside is like 3 to the 0. It's going to be the identity, and the additive identity is just 0. 3 to the 1 is 3. 3 squared is 3 plus 3, because we're doing the operation twice. 3 to the 3 power is 3 plus 3 plus 3. 3 to the minus 1 is -3 because it's the inverse. So 3 to the minus 1 just means the inverse, and the additive inverse is -3. 3 to the minus 2 is going to be -3 plus -3, etc. Okay, so then this set is just going to be, it's got -9, -6, -3, 0, 3, 6, etc. Maybe I should make this a little bit clearer by saying this is the answer. And this other stuff that we just did, this was just some sort of practice computations to get to the answer. So maybe I should move this in a little bit. Okay, and this actually is a subgroup. And so how can you tell? Remember, the things we need to check for a subgroup is the identity of the original group in there. Well, the identity of the original group, Z under addition, is 0, and there it is in the subgroup, so that's cool. What about for every element, is there an inverse? Sure, like if I pick 3, -3 is its additive inverse, that's in there. 6, -6 is its inverse. -9, +9 is its additive inverse. Everybody has an additive inverse in there. And then closure, well, if I take a multiple of 3 and I add another multiple of 3, I'm gonna end up with a multiple of 3. So this is closed. So this is an example of a cyclic subgroup generated by G. Move this down a little bit. All right, so let's talk about, ooh, that's too much. Let's talk about cyclic groups. Sorry. So sometimes when you choose an element A and you consider the cyclic subgroup generated by A. Oops, sorry. Sorry. Oh, not Siri. Go away, Siri. So sometimes when you pick an element A and you ask for the cyclic subgroup generated by A, you get a subset, a proper subset. It's not all of it, it's just some of it. But sometimes for some values of A, maybe it turns out that you get the entire group. So if that happens, if there's an element of the group so that G, if you take that cyclic subgroup, you actually get all of G, then you call G to be cyclic. G itself is a cyclic group in this case. And in that same case, then you say A generates G. So it's kind of like, those of you who had linear algebra, which is most of you, so do you remember a spanning set? So if you had a vector space and you wanted to have, so a spanning set was a set of vectors so that you could use those vectors to produce any other vector in the space just by taking linear combinations. So they were kind of like sort of a base level of things that you could generate everything else from. Okay, that's just what a generator is here. It's something that if you just take this one element and combine it by itself as many times as all the different possible numbers of times, then you generate the whole group. Okay, so for an example, well, let's see. So what if I consider the integers? So let's say G is the integers. If G is the integers, then, well, G can be written as it's generated by 1. Because 1 plus 1 is 2. 1 plus 1 plus 1 is 3. The additive inverse of 1 is -1. So everything's going to be in here, generated by 1. But also, it's generated by -1. So A equals 1 and B equals -1 are both generators. or G. Okay, or if I consider this example up here, 3, I mean, that makes sense, right? It's generated by 3. 3 is a generator for this set. Okay. Okay, so here's another question. So what about these? We know these groups. These are the two 4-element groups. Let's try to decide if either of these are cyclic, and if they are, what's the generator? So, well, let's see. If I look at, I keep doing that. If I look at this group, 0 isn't a generator, because if I add 0 to 0 to 0 to 0, I just keep getting 0. What about 1? If I take 1 and add it to 1, I get 2. If I take 1 and add it to 1 and then add it to 1, I get 3. If I take 1 plus 1 plus 1 plus 1, I get 4, which is 0. And then I cycle it around. So actually, 1 is enough to generate this whole group. So this is cyclic. Z4 is cyclic. And in fact, it's generated by the number 1. Also, this might be fun to look into. Is it generated by anything else? Is there another element of this group that is generated by? Think about that for a minute. Or maybe I'll give you a big hint. Could it be 2? Oh gosh, keep getting that confused. Could it be 2? Well, see, if I do 2 plus 2, I get 0. 2 plus 2 plus 2 is going to be 0 plus 2, which is back to 2. So I just go back and forth between 2 and 0, and I never get 1. So the subgroup generated by 2 does not have 1 in it. So that's not going to be a generator of Z4. But let's think about the Klein group here. Is this cyclic? Well, let's see. If I take A, if I think A might be the generator, if I multiply A by itself, I get to E. Oops, and then E times A is A. I just go back and forth between A and E. So that doesn't generate, doesn't give me a B or a C. Same thing for B. B times B is already E, and so I don't have a chance to get A or C. Same thing for C. So actually, this is not cyclic. B is not cyclic. Because V is not the cyclic subgroup generated by A, and V is not the cyclic subgroup generated by B, and it's also not the cyclic subgroup generated by C. So this only contains E and A. This only contains E and B. And this only contains E and C. So these 3 subgroups actually, these subgroups are cyclic, but the full group is not cyclic. Where'd this go? Here, this full group is cyclic. And here's a generator. It also has a cyclic subgroup, which is just has 0 and 2 in it. Okay, that's all I have to say about cyclic groups. I'll see you later.